So what I'd like to do is, if there's no more questions, I'd like to continue talking about briefly about cleaning before data cleaning before going on to another subject. And we talked last time about missing value prediction. We talked about unifying things. One aspect of data cleaning that is important to think about is this problem of outlier detection. So often you get values in a data set in a particular column that are unusually large or unusually small. For example, I was once reading an article about dinosaurs, okay, and you know, what do you know about dinosaurs? I assume you know dinosaurs are big, okay? Well, the American Museum of Natural History in New York has what you call it, the one of the best collections of dinosaurs in the world, and I encourage you guys to go visit that sometime soon. But one thing that's interesting is that among their records, when they look at the size of dinosaur vertebrae, the backbone, these bones in the back, the largest dinosaur vertebrae ever found was 50% larger than any other dinosaur vertebrae ever found. Okay? And there's a record of this at the American Museum of Natural History, this giant dinosaur vertebrae. Now, why is it 50% larger than any other dinosaur vertebrae ever found? And the answer presumably is it was a data error, actually. It seems like the museum can't locate this specimen anymore, okay? But somehow it's written in a record that the dinosaur vertebrae was measured as this big. Quite often when you have something that is much bigger or much smaller than anything else in the column, it reflects some kind of a reporting error, a measurement error, something, okay? And this is kind of an encouragement that when you are doing these things, okay, you need to look for outliers, okay? And again, we've talked about distributions and how it was, you can't have too much mass, probability mass too far away from the mean in terms of standard deviation. These bounds are particularly tight in terms of normally distributed variables, okay? In general, the probability that if we figure out how many samples should we expect to see if we break the distribution into distances based on the standard deviation, sigma, 2, 3 sigma, 4 sigma, okay, you will not have large deviations from the mean. In human height, what is the mean human height? Okay, I picture, what is it? Let's say 6 feet. That's more like 5.5 feet. What is the standard deviation of human height? I'm going to guess something like about 6 inches. Okay, can we have someone who is 14 feet tall? The answer is not if we only have 7 million people on the planet, okay? And likewise, anything that if you have something that's normally distributed, anything that's too many sigmas from the mean is a problem. And my encouragement is that you figure out why you have outliers, okay, if you can. It's usually a bad idea just to delete the outlier value if you see one there. Usually there's a systematic reason, and it's important to try to figure out why that is. Any questions? So how do you identify outliers? Well, if you have a picture, it is usually easy to see the points that are outliers, okay, because they are far from the cluster centers. But that usually only works in low dimensional spaces because we can only see things in 2 dimensions or 3 dimensions. What I would probably say is one good way to try to detect outliers is going to be to try to take the data and cluster it. Usually data will exist in natural clusters of points. The outliers are the ones that are kind of far from any cluster. And so one way to measure, identify potential outliers in higher dimensional space might be to cluster the data points, okay? Find the center of each cluster. And then for every point, keep track of what is the distance to the nearest cluster center. If that distance is large, that is probably a good candidate for an outlier. Any questions about that? Okay. So one question that will come up, in your data set, have you guys got any kind of unusual outliers that you guys have found in your data set? Data set might be a product that is wildly too expensive or wildly too cheap, or is selling a wild number of things. Okay. Any of those come up in the data set that you have? I'm not hearing the sound of it.
Yeah,
Okay.
there was one with very unusually high amount of price, and then in the sales as well, there were two outliers. But then after looking at the data a bit, only one of them seemed to be the outlier.
Okay, so you said one that was an outlier on price. What was the price, and why was that? In what way was it an outlier?
So in the box plot, so I think the price of that outlier was more than 3 lakhs, so that's $350,000, and the highest in the entire data set was around $75,000. So
Okay, so you said one object that was $350,000, where
yeah,
the nearest other thing was $70,000.
yeah,
Okay, that
definitely.
might be a cause for suspicion. Um, a lot depends upon what the distribution is and what was the object. Did you find out what the name of that object was?
Yeah, I'll check.
What was it?
I have the item ID. I didn't check the name.
Okay, something like that. To tell whether it's an outlier, I'd like to tell what the name is. If it's a car, if it's a luxury car, that's not unreasonable. If it's a book, that's probably unreasonable. Okay, so and you said that on sales there were a few outliers. What kind of sales did you have?
Yeah, yeah. So the maximum should be 750 per day, but there were two outliers. One which had 1,000 and other around 2,500.
So one thing that's sold wildly more, okay?
Yeah,
And there's again, it's a question of, is there some kind of mistake or is there not? You know, every once in a while, for example, there is a pricing error on Amazon where somebody enters the guy working there enters the price, as being 100 times lower than it should be. Certainly this happens in airfare pricing from time to time, where suddenly the airline will wake up and wonder, why was there such an increase of demand between flights between New York and Hong Kong last night? And the reason is because someone put there that the price was $13 or something like that. Okay. Anyway, when you're building these models, are you better off, okay, deleting the outliers before fitting?
so one of the items, so I checked the entire sales of that item. So for the item which had sale around 1,000, it's usually it occurs that in other shops it had a sale around 500, 600 per day. So that was, I didn't remove that outlier, but then for the 2,001, it was a one-time sale. So I removed that out. I deleted that.
Okay, so the question of why is something an outlier and what should you delete it? Okay, the good thing about deleting outliers before you fit is that you can come up with a model that is going to have a lower error on it. Okay, if you can get rid of all the outliers, okay, it's usually easier to predict the things that are, are not outliers. By definition, an outlier is something unexpected. If you get rid of the things that you don't expect, you should be able to generate better predictions. It should be easier to model, okay? So certainly, if you've got points that are corresponding to measurement error, okay, or some kind of a real error, then you're probably much better off trying to fit the real data and not try to fit the data. On the other hand, people are often very, very happy to delete outliers before they do their fitting, or certainly in their evaluation, okay? Just because they make the score bad, okay? And note, again, it's kind of important to note that you will get a worse model, okay, if you delete outliers that are real things as opposed to error. And that's why a certain level of judgment here is necessary to know when you should remove something or when you shouldn't, okay? Any questions about that?
Professor, so in this example, the one outlier that we had was because it was a one-time sale and that item didn't have any other sales. So it was easy to recognize this as an outlier. Whereas for the first item that looked like an outlier, it made sense for it to have high number of sales because it was at an all-time low price. So this kind of makes sense when we have very small number of outliers and we can visually see this. But I'm assuming there would be a situation where there would be a lot of outliers. So how do we understand at that point which one is a genuine outlier and which one should be kept in the data?
So what might be one strategy? Well, if you're telling me that the special case of one-time sales, I mean, it's an object that was only offered once. Is that what you're actually, is that in the example that you're talking about? It was an item that was only offered one time.
Yeah.
Well, it might be that the general class of objects that are offered only one time might be something that you don't want to predict the same way you predict other objects, okay? Yeah. That you might want to kind of identify that as, for example, a special class of sales. Is it, again, I don't know what this store is like. Does this store regularly offer one-time only sales, okay?
No, it was unique to this product itself.
Okay, then, that may or may not be, so what I would be trying to do, first of all, is to see whether there is a general explanation for the kind of outliers that you're dealing with. If what you're saying is that when the price goes down dramatically, sales go up dramatically, that certainly seems like something that you would not, that's not an error, that's sort of something you would want in your model. Okay, the one-time sales may be very difficult things to predict, and they may be weird enough relative to the general class of things that you might want to segregate them out, okay? This is a judgment call, okay? Any questions about that? Like one thing when we were talking last time about was, in where I remember we had outliers. When I told you we were once working with Wikipedia data and we wanted to understand people, and I was worried about things about their lifespan. Well, one thing that we noticed was that there were people in Wikipedia who have lifespans up to 969 years. Who is it who has, in Wikipedia, who has a lifespan of 969 years? Does anyone know?
Is it like Abraham?
Yeah,
Abraham only lived to 120 for what it's worth. But
Methuselah was
Noah,
I think, lived to 600, okay? But we keep going. Has anyone ever heard of Methuselah? Methuselah was a biblical figure whose entire role in the Bible was that he lived to be 969, and then he presumably begat people, okay? So, if you were looking at building a model related, and you had these figures where they were listed with these kind of ages, okay, what should you do with them? Okay, you could treat them like normal people, or you could sort of realize that, well, maybe biblical figures are fictional, are presumably fictional figures, okay, who, these numbers are not analogous to what people are, right? So maybe we treat anybody with lifespans above a certain, amount as a separate case, okay, as fictional figures, okay? So anyway, these are the kind of issues that come up in dealing with outliers. Any questions?
About the data set that we're using for all the products, a lot of them, or in the last lecture, we were talking about trying to remove artifacts like the USA versus the United States of America as the label, how they were the same thing, but they had different titles on them. Half of these are in Russian, and I can't read them. How do you do that?
Okay, so first of all, you should, again, I encouraged you to translate these into English when you can, okay, to use a translator. What you might be saying is the translator is failing to translate certain terms. Is that what you're telling me?
I didn't try translating them because I just didn't trust Google Translate. I can try that though.
Okay, again, it would seem to me that unless you have better knowledge of Russian than I do, okay, you would be better with these things translated, and you will have a better understanding of what's going on. Okay, any questions?
Professor, if I may, this just reminds me. So when I converted this shop names to English, so there were, I think, 2 or 3 shops, which are, I think there are duplicates in the data set because a few shops are just named different. So let's say it's shop 1, and there's another entry in which there's a street name first and then shop 1. So the same shop, but different way of writing its name. So I didn't know how to deal with it. So.
Okay, I am not sure I'm capturing this.
Okay, so there's a single shop which is written in 2 different ways. So its name, which is shop 1, and then the other way of writing the same shop is the street name and then the shop name. So let's say there's shop 1
Okay,
and then
so one question here is, so I'm hearing you do this. One question is whether that's the idiosyncrasies of a translator or whether it is one shop that has 2 names. Okay, if it's the idiosyncrasies of the translator, it probably doesn't matter. If the shop is identified by a key, and the key of the shop is really what matters, okay, then maybe the fact that the translation is not consistent, okay, may be an artifact, okay? This, I don't know, this you have to reason about, okay? Okay.
Assuming it was the same shop, how do I deal with it?
So if you have one shop with 2 different names, okay, there is a question of, wait, so first of all, if you have 2 things that you are convinced are, that have slightly different names that you're convinced are the same thing, if you are looking at the papers published for Stephen Skeena and Stephen S. Skeena, then usually you would aggregate it, okay? Is that what the problem that you have here is?
Yeah,
You have a suspicion that the same thing is under 2 different names?
Yeah.
If so, then you would aggregate it. That would be a natural thing to do, okay? You have to be, convinced you know what your suspicion is.
Okay.
Any questions?
I have a question.
Yeah.
So you said that we should not delete the outliers before fitting the model. But once I have done, say, 1 round of my model fitting, and I want to tune it further, and then I want to remove certain outliers, and I see that my model is performing better. I mean, is it fine to remove the outliers then? Because
okay, again, an important thing to see is, are you doing better on the what you call it? On the are you doing better on the test data as opposed to the training data?
Yeah, I meant the test data.
Okay, so that might, again, you could imagine a world, let's say that your data came in and it was made a quarter of weird things that were completely unexplainable, and 3/4 of things were explainable. Okay?
Yeah.
If you could find, if you tried to model both of them by the same model, you could very well, your model might be fooled by that. Okay? And what you call it? So that is conceivably something that's happening here. Okay, that maybe there are unpredictable things that are really outside the bounds of what you could hope to capture. Okay, under those conditions, it might pay to remove the outliers and try to fit it. Okay, again, this is why one does experiments. Okay, any questions?
I was just
The judgment that I would say is, am I going to do better on the withheld test data? Okay, that's usually that's intended for how you will avoid the sins of overfitting. Okay. Any questions? Okay. What I'd like to talk about now are what you call it. Let me try something here. Give me 1 second. No. Okay, I'd like to now change subjects to a question of dealing with scores and rankings. Okay, that quite often. Okay, what I mean a scoring function is a way of reducing a complicated multi-dimensional data record to a single value to try to highlight some kind of properties of this. Okay, so many of you are familiar with what you call it, rankings of things. My guess is many of you are at Stony Brook because you saw rankings of colleges, okay, or graduate schools. And Stony Brook appeared 41st on this list. The other schools you got into were 72nd and 193, and so therefore you came to Stony Brook. How many people used the rankings of colleges to help choose whether you came to Stony Brook? Are there any of you who will admit to that or not? Some of you say no. Okay. I suspect some of you actually did. It's funny. Sometimes I get a view of whether people are saying yes or no. And at this moment, I am not. But anyway, it's certainly the case that when you see football teams ranked, again, we're in a world of college football. Usually you rank the top teams in college football, and those are the best universities in the country, at least in the football world. Okay? The question is that how do we come up with a ranking from 1 to N of schools, football teams, baseball players, stocks, whatever you want, okay? Usually what you do is you compute some kind of score, a number that takes all the data values of the thing. Maybe for schools, it might involve, what you call it, how many students go there, what were their GREs, what was the salaries that they had that they got on graduation, what schools got rejected by people who were going to this school, okay, what schools were accepted ahead of this school by students. You would like to reduce that to a single statistic, which we'll call a scoring function, and typically by sorting these scoring functions is how you would build a ranking. Okay, any questions? I assume everybody's familiar with these kind of rankings. Now, what I would say is that I think of the grades that I assign people at the end of the semester have the same properties of these scores that you typically get, these ranking systems. And what I would like to kind of point out are a couple things about grades. Okay, all of you have taken dozens of classes in your life. All of you have had teachers who've assigned grades. All of them use different methods. Some teachers will end up trusting the homeworks more, weigh the homeworks more than the exams. Some people will weigh the exams more than the homework. Some people will weigh class participation. Some people will weigh attendance. Some people will use group projects and somehow try to disambiguate. Some people will do this individually, okay? Every teacher you have ever had has had a scoring function mapping your performance to a grade. One thing that's clear is that every teacher does it differently, okay? So there's a certain amount of arbitrariness in building a scoring function. It's also interesting that there is no validation data, okay? You guys are used in machine learning. You say, oh, I'm going to have a test data. I'm going to have a training set. I'm going to try to build a good model on my training set, and I'm going to validate it by comparing it to the test data. What are the right grades that I should give you guys? There is no right answer to that. Does everybody kind of see that? That I have a grading system. It's a score. It's a statistic that takes all the data I have about you and produces a number about it. The interesting thing is that there is no right grade. There's no way you can kind of objectively go to tell me that my grading system is less good than the grading system Professor Stark did, okay? There's different, different formulas, okay? But there's no validation. Still, what I'd like to convince you is that, in fact, despite the fact that every teacher uses a different system and no grading system is validated, okay, there is still a general robustness. Most of you, I trust, get good grades in just about all your classes, okay? You could imagine a world where if you were a B student, a B student might get all A's and all half A's and half C's, but that usually isn't what happens. Usually people get relatively consistent grades across all their programs, which tells me that there's a certain level of robustness in this idea, even though they use arbitrary formulas, even though they don't have validation, okay? If there's an attempt to try to come up with a formula that they think correlates with quality or effort or performance, they're probably going to get a decent job done out of it. And that's kind of the philosophy I want us to think about with scoring functions. We want to try to take a data set, reduce it to one value that will kind of characterize the merit of the of each item. Any questions about that? Okay. So again, just to not beat a dead horse, but to say it one more time, the critical thing that I think is the difference between something like linear regression, which you guys are probably using on your homework, okay, is that you kind of know what the right answer should be on certain records. And you're trying to come up with a function that realizes the, to predict that value. You have kind of what we would call a gold standard to what the right answer is, okay? Now, generally speaking, in applications of trying to find a scoring function, we usually do not have a gold standard. Now, there are some ranking applications of ranking where you do know what the right answer is. You know, the most famous ranking algorithm in the world is Google, which somehow for every query will rank all the pages of the internet from most relevant to least relevant, okay? And, you know, did they do that based on just an arbitrary scoring function? Well, Google has data. They know that when they flash up a page of links, they know that people should usually, if their scoring function is right, the one that they're going to click on is going to be the top one. If someone clicks on the second item instead of the first, that's probably a sign that Google got the ranking wrong. Okay, that what they, you know, that they know based on which links you clicked on, You have insight as to when the ranking function was right and when the ranking function was wrong. So in these cases, yes, you can design a scoring, a regression-like system, a machine learning system to try to predict what the ranking should be. Generally, we don't live in this kind of a world. Any questions about that? So one example of a scoring function that I like as a representative of something is the body mass index. Has everybody here heard of the idea of body mass index, BMI? Okay. BMI is a statistic that is designed to capture whether or not you are heavier than you should be. Okay. And the BMI is a statistic where they take your mass in kilograms and your height in meters. The BMI is the mass in kilograms over the square of the height in meters. So when I made up this slide, I had a body mass index of 22.8. Is that good? Well, it's a normal. It's probably getting a little bit closer to overweight than I'd like it to be. Okay. But does everybody kind of see that this is a number that if you are heavier than you should be for your height, the BMI is going to be large. And there's a standard scale for interpreting these things where, if your BMI is under 25, you're presumably not overweight, but 25 is where it starts to be overweight, and obese is when your BMI was over 30. There was a news report about Trump at some point when he was running the first time, where he gave what his weight was, and then suddenly at one point his height suddenly grew by an inch, and that inch was enough to move him from the obese category into the the overweight category by BMI. Any questions about BMI? Does everybody see that this is a scoring function? It takes measurements about you and produces a one-dimensional number. Okay? Any questions about that? Is it a good or meaningful number? Okay. Why is this the height squared? Can anybody tell me why the height squared appears in BMI?
Because height cubed was too much, and height 2.5 when they initially did it was too complicated to calculate, so they made it height squared.
So, if you think about it, the BMI, if you're measuring some kind of density, it should be mass over volume. That isn't quite what this is, okay? Basically, this was an arbitrary decision, and you will hear various doctors and public health people say, no, BMI is not the right statistic, not the right statistic. But what's good about it is it's simple to calculate. It has a meaning that people can keep in their heads, and it does interesting things, okay? Here I showed you, I did a dot plot of BMI of basketball players and American football players. What do we know about basketball players? Does anybody know anything about basketball players?
Very skinny.
They're very what?
Skinny, lanky.
Skinny and lanky. I would say tall and in good shape. They run up and down the court for a living, right? So if we look at this thing, how many obese basketball players are there? Here I have a world where I did a dot plot where the x-axis is their weight, the y-axis is their height. Notice in comparing these figures, the heights are substantially bigger of basketball players than football players. But I had them colored whether or not they were of normal weight or overweight. And almost no professional basketball player would be obese. Many of them are what would be listed as overweight, okay? But that's actually because they've got a lot of muscle. Notice that if I put on a lot of muscle, okay, no fat, but a lot of muscle, I will still have a lot of mass. Compare this to American football players. What do we see when we look at the dot plot here? The vast majority of American football players, okay, score as obese. These guys are animals. They sit there, you know, they're very designed to be, there's certain positions where their job is to basically not be movable. They're supposed to block and prevent other people from moving. If they are big and heavy, no one can move them. Okay, does everybody see that relatively few American football players would qualify as being of normal BMI? Okay, maybe maybe they would be, maybe they're the kickers, maybe a few quarterbacks, something like that. Any questions? Okay, my claim is that the BMI is an interesting statistic. It's revealing, it's easy to compute, okay, and this is the kind of thing I like to think we aspire to as a scoring function. Any questions about BMI? So this question of living in a data world without a gold standard is kind of an important thing to recognize. That somehow, again, I think of as a gold standard as being a label that kind of is assumed or trusted to be correct. This is a human annotation. This is kind of what you want to predict. What I claim are proxies. A proxy is a quantity that that can be measured, that we hope is correlated with what we hope is correlated with what we really want. When a college is trying to admit you, they are trying to get a measure of how good a student you are. We want to admit the best students. Now, is your GPA in high school a measure of how good a student you are? The answer is yes. Is it a gold standard? Okay. What would happen if we admitted all the people which had the best GPAs? Okay, would those be the best students? They might be the students who took the easiest classes. They might be the students who went to the lousiest university. Okay. What about SAT or your GRE score? Is that a proxy for how good you are, okay, as a student? Well, there's a correlation between GREs and certainly for undergrads between SATs and college GPAs. Actually, recently people have been finding that for GREs, the correlation between college performance and that is weaker than they thought, okay? That's why some people suggest dumping the GREs, okay? But recognize that there's a distinction between a world where we have a right answer and where we have something we can measure, okay? Usually we have to make decisions based on what we can measure. A scoring function combines things that we can measure, okay? If we don't know what the truth is, okay, then we're in the world of statistics rather than machine learning. Any questions? Okay, I think that's all kind of obvious. Okay, and basically just to rephrase what I'm kind of saying, okay, if you have a gold standard, you've got a machine learning problem. If you have a proxy to what you want, all you can do is basically compute a scoring function on that and hope for the best. And again, we'll talk at the end of the semester about some ethical things, about how you should interpret data. There's a very, very interesting book called Weapons of Math Destruction, okay, which is about bad uses of data science, okay? And one of the classic ones is, that kind of has had resonance on Long Island, has to do with how do you evaluate teachers, okay? You know that in the United States, schools are trying to hire the best teachers that they can, your elementary schools, your high schools, and things like that. They want to fire the teachers that are not good teachers. How do you tell if someone's a good teacher or not? Often what they will try to do is, in order to try to get human bias out of it, or for various reasons, someone will come up with a statistic to try to measure how good the teachers are. Like, what was the test score performance of the students that were in their class, okay? Again, you get problems when you use something that is a proxy, like student test scores, which reflect the quality of the students coming in, as opposed to teaching, which is probably something that's hard to measure, okay? Any questions? Okay, good. Okay, so when we have data, we kind of agree we can take a scoring, a bunch of statistics and compute a score from it, okay? Typically a linear combination or something like that. We could sort these scores to get a ranking for where you rank in a cohort. Which number is more interpretable? A raw score or a, a ranking? When I did this slide, there was a measurement of the quality of a basketball team called RPI. Stony Brook at that point ranked 111th among 350 teams in college RPI, with an RPI of 39.18. Which number is a more meaningful number to you? Is it the RPI or is it the ranking?
The ranking.
Okay, who here finds ranking to be more meaningful as a number in isolation? This tells me, okay, is Stony Brook a great team? No. Is Stony Brook a good team? It was an okay team actually that year.
What is
Okay.
RPI?
What is RPI? RPI was I don't even know what the name of that. Probably it's like reputation power index or something like this. It was a statistic that some website computed on the quality of teams. Okay. How would you rank the quality of teams if they were ranking basketball teams? The winning record is probably the won-loss record. How many times did they win? How many times did they lost? Probably matters. Is that the only factor in judging whether a college basketball team is good or bad? What else should that consider?
Individual players.
What?
Individual players.
Individual players, so you might want to get scores or measurements of how good the players are? Maybe. What is going to be a limitation of the, just having the one-loss record among teams?
The teams might be playing different opponents.
They play
So
different opponents. Okay, I believe the speaker at one point was a student at Duke. Am I correct?
yes,
Duke, what do we know about Duke? Duke has a great basketball team. And why does it plays other great basketball teams? If Duke has a record of 20 and 10, it's one of the best basketball teams in the country. If Stony Brook has a record of 20 and 10, where does it rank? Down here, because we're playing against the School for the Blind and all other, we're not playing against prominent teams, okay? So there's more, trying to come up with what does the scoring mean. That's what a statistic like this would try to come up with. One question that's interesting is, suppose, let's say you wanted to get an idea of the distribution of scores. What do we think, let's say I wanted to know how much better number 1 was than number 2. For this, I would be interested in the distribution of the scores. Does everybody kind of see that if you have a scoring function, okay, you would probably expect that it's going to have a few teams that have extremely good scores, a few teams that have extremely bad scores, okay? But there's probably a lot of teams that are kind of clustered around the middle. you know, there is usually, we would expect a bigger difference between the first, well, which one do you think? Do you think that there's a bigger difference between the first and the second ranked team? Or the, it looks like 170th and the 171st ranked team? Typically, if there's a bell-shaped distribution, you would expect that the teams that are close, that are you know, ranked in the middle, there's probably very little to tell them apart. Okay, and so if you want to get a sense of, you know, kind of how much better a team is than another, the rank is not necessarily the right thing. There, you might be interested in the individual scores. Any questions about that? Okay, so sometimes the scores are what is interesting, like BMI. Sometimes the rankings of those scores is more interpretable. Any questions? So what is an example? What are the properties of good scoring functions? One is, I think they should be easily computable. It's important that they be easily understandable. Okay, if you are going to, you know, people talk about, you know, when they talk about AI, there's a lot of concerns about interpretability. Usually a scoring function is easy to, you know, can be properly interpreted if you understand where it comes from. Okay? If it treats the variables in kind of like a monotonic way, usually if you're building a scoring function, you want features with the property that it's clear what values are good and what values are bad. If I have your GPA and I'm rating you based on your GPA and your SAT score, higher SATs mean better students. Higher GPA means better student, okay? If I want it also had a statistic like, you know, kind of, what might be something I would have on a student that would not necessarily have a monotonic interpretation. Any ideas? Okay, I'm getting myself in trouble. Okay, obviously if I had their zip code, it's not clear that the zip code tells me anything. Okay, sometimes if I had, you know, anyway, you want variables with the property that you know what is good and what is not good. You should check the outliers, the unusually absolute best and the absolutely worst ranked people, and see whether they make sense to you. And it's important that you use a normalized variables so that when you're combining them in a sensible way. Generally, you know, a good way to normalize variables is this idea of a z-score, which I mentioned before. The z-score of the ith observation is going to be the value of the ith observation minus the mean of the observation divided by the standard deviation. Okay? What's great about z-scores is the mean value of a z-score is going to be 0. Okay? Negative values mean what you call it, the items that are below the mean. Items that are positive values means the value is above the mean. Okay? The standard deviation normalizes it. So the standard deviation of the z-scores is actually 1. So all the variables now have identical means and a similar spread. And things like changing units will not affect z-score. So if I measure your height in inches or miles, your z-score in a cohort is still going to be the same. Any questions about that? Okay, Fumi, what?
Hi, Professor. The comment about the previous slide, I wonder how much of an impact would it be to release the scoring function would releasing the scoring function impact the quality of the metric itself,
By
such as the ranking,
releasing the scoring function? I mean, how you compute it?
such as the Google search rank algorithm or the college ranking algorithm?
Okay, there is a score, you know, there are sort of laws of the world. I don't know if you guys have ever heard of Murphy's law, that, you know, that or the Peter principle, that's kind of governs sort of how the world works. There is one of those laws, Goodhart's law, I think that's what you're now pointing out, which I believe means that whenever something is used as a metric for making judgments, it stops working as a judgment. Okay? When Google was trying to rank the pages from best to worst, it was trying to you know, produce what were the most meaningful signals and identify and reward the best pages. Once there is a criteria, scoring criteria, then you would expect that what you call it, that various people are going to try to get as high a score as they can, and they're going to do things to pervert the statistic. What do we know about what you call it? If you know that the scoring criteria to get into college depends upon your GPA and your SATs, once that's well known, what do we try to pervert it? Well, people start taking special classes just to improve their SAT scores. They start hounding their professors and teachers to give them better grades because the GPA means something. So to a certain extent, once you have the metric, or the point that you're making is, once the metric is known, okay, then and if people are working to try to do better by that metric, it no longer does as good a job of evaluating performance as opposed to evaluating how much they're cheating, you know, how much they're trying to realize this metric. Okay? That's a problem orthogonal to what we're dealing with right now. Any questions? Okay. So again, with z-scores, the important thing are that the mean of the z-score is 0, and the standard deviation is 1. Okay, and this enables us to compare different variables in an analogous way. So let's say I wanted to come up with a performance metric for you as a function based on your SAT scores and on your GPA. GPAs typically lie between what? They go between like 1.0 and 4.0, or in some perverted world where they rate, you know, maybe give A pluses, maybe it gets as high as a 5. SAT scores, okay, would range from, let's say, 200 to 800, okay? How are we going to build a score based on combining GPAs and SATs? We could try some arbitrary thing like, well, it looks like the range for SAT scores is up to 800. If we took your GPA and we multiply it by 20, now the range goes to from actually 200 to 800. So maybe that sort of does it. But a more principled thing would be to compute your z-score in your GPA among your cohort. And now I will have a positive number if your GPA is better than average and worse if it's not. And if I did the same thing on your SATs, I'll have a positive value if you're above the mean and below the mean. And the spreads are going to all have standard deviation 1. It's perfectly reasonable to average the z-scores or add them up to get a combination of these two variables, okay, in ways that it's a lot fishier if you try to deal with it, the normalization in an ad hoc way. Any questions about that?
I was just thinking, like, standard normal distribution also has a similar property, like having mean of 0 and sigma of 1, and we do the same thing, like subtract the data points by the mean and then divide by the sigma to get the standard normal distribution. So is it in any way?
That's actually exactly true. What z-scores are trying to do basically is take your hopefully normally distributed data and map it to this standard normal distribution. That's exactly what a way to interpret what the z-score is.
Is it
Okay.
exactly the same, or do we just have like different names, z-score and
Well, notice that just doing a z-score transformation is not going to make your data normally distributed.
right?
Okay. Suppose, let's say we had a world where our data, the distribution of our data looked something like this.
Mm-hmm.
Okay. If I now take the z-scores of these values and I plot it, the distribution is going to look exactly the same.
Yeah.
Taking the z-score is just a linear transformation, right?
Yeah.
So it doesn't change the shape of the distribution, okay? It just brings it to a realm where different distributions are kind of sort of the same magnitude. In an ideal world, our data would be normally distributed and it would work exactly the way that you're talking about.
So we can say
Okay.
that z-score maps for distributions which are not normal, but
So the z-score is still something you can compute on a non-normal distribution.
okay.
Okay, it will still have, if we did this, what's now going to be the case? Probably this is where 0 is going to be. Okay. These are going to be negative values over here.
Mm-hmm.
Okay.
Yeah.
It still tells you something in that the range is going to be more consistent with other variables, and it'll tell you what's above and below the mean. But if it's still got a weird distribution, it probably won't function as well as a feature as if it was a more normal distribution. Maybe if I took the log of this, then it would look more bell-shaped, and then I took the z-score of it. Maybe that would be a better feature to have. Okay?
Yeah.
Okay, any questions? Okay, good. Okay, so I'd like to talk now about some ranking techniques that that we can use to compute kind of scores, rankings for items under particular data sources. And one source of data that we often have in trying to build rankings, okay, are binary comparisons. If I want to try to identify which is the best football team, okay, often I will know not only how many wins and losses, okay, did I have, but I will actually know which team beat which other team. Okay, this tells me something. If Stony Brook beat the School for the Blind, okay, that shouldn't count for very much. Okay, if Stony Brook beat, in football, beat Texas, well, that would be a miracle. Okay, and that tells you that Stony Brook would be a really good team. Okay, you get binary comparisons data quite often if you look at it. If I wanted to try to rank universities, okay, many of you, before you came to Stony Brook, got admitted by some other school, okay? If you got admitted to Buffalo and you got admitted to Stony Brook and you chose Stony Brook, that is kind of a vote that given the choice of Stony Brook or Buffalo, you voted Stony Brook, okay? If you want to try to rank universities, interpreting the data like that as votes is an interesting thing, as these binary comparisons. If you ask experts, okay, is this football team better than this football team? Which is how football rankings are done, okay? Those votes are binary comparisons, okay? And in general, vote counts are useful ways of ranking things, but they fail when people play different levels of competition, okay? And that motivates a ranking system called ELO. ELO is a scoring system where we picture a world where if we want to rank n items, we'll start out by assuming each of them are equally ranked before we have seen any observations of wins or losses. Maybe we'll give each one a starting score of, let's say, 1,500, okay? Then every time we have a match, a comparison between two items, we're going to adjust the scores of the people people in the comparison. The new ranking for player A is going to be the old ranking of player A plus a change depending upon what the outcome of a match is. If UA is the expected outcome, let's say the expected outcome for a match, okay? Whether I am playing someone who I should expect to win, beat, or not. And S sub A is the actual outcome of the match. If I won the match, okay, I get a score of 1. If I was predicted likely to win, my expected chance of winning the match was neutral, okay, I was playing somebody of my own ability, that would mean that 1 minus 0 would be 1, and my ranking would grow by k points. In general, we're going to have S sub A is the score of the actual comparison. Minus 1 means that A lost, plus 1 means A won, and this is the expected result, okay? This parameter K modulates how much the ranking should swing, okay, on the basis of one match. Any questions about that? So the question of how much my ranking changes depends upon how much better or worse I did than expected. Does everybody kind of get that idea? This expected value of my performance in the match should depend on the score of me and my opponent, okay, as to whether I would be likely to beat them. Any questions? So what are we going to say the expected value for me in a match should be 1 times the probability that I beat you plus minus 1 times the probability you beat me, which is, I guess, 1 minus the probability I beat you. Okay? If we can find a way to predict what the probability of me beating you is on the basis, on the difference of our rankings, this gives us a way to adjust rankings based on the result of a match. This gives us a way to measure our surprise in the outcomes based on our current scores. Any questions about that?
On the previous slide, when we were talking about predictions, what's the difference between, where it says like mu is the expected score from the previous RA, what's the difference between mu and RA?
RA is my ranking, okay? This is an arbitrary number, okay? It's a score measuring how good I am, okay? And mu A is the probability that I'm going to win in my next match, okay? This should be a function of the ranking. But my probability, remember, my ranking, I started out with a number of, say, 1,500 arbitrarily, okay? My expected value of winning the match is based on what's the probability of me beating the guy and what is the probability of me losing to that guy, okay? So mu A is defined as again, it's 1 for a win minus 1 for a loss. Okay? Any questions about that? Does that answer your question?
I think so. I'm not clear how the probability is calculated, but I think it makes sense.
Oh, but that's actually a good question. How is it that we calculate that probability? Okay? What is the probability that I'm going to beat you? Okay? It shouldn't be clear because we haven't discussed it. Okay? What should be clear is if I have a score for me, let's say my score was 1581 and your score was 1492. Okay? If higher scores are better, I should be favored. The probability is that I'm going to win. Okay? It should more likely that I should beat you. But how much more likely? I need a function that maps the difference of our scores to a probability. And that score, that function, is what we call the logit function. Okay? The logit function is defined like this, 1 over 1 plus e to the minus z. It's a function of one variable z. This is the difference in our rankings. If the difference is huge, e to the minus z, what is e to the minus z if z is very large? That's 1 over e to the z. 1 over a huge number is 0. If z is very large, the probability of me beating you is 1. Okay? If z is very, very small, okay, it's a negative number, okay, then e to the minus minus z is a huge number. 1 over a huge number, okay, is 0, okay? If my score, if the difference in our scores is incredibly negative, I have no chance to beat you, okay? This logit function has the property that if there is no difference in our scores, okay, namely it is 0, e to the 0 is 1. Therefore, the logit function is a half when there is no difference in our scores. As the difference in our scores gets bigger and bigger, the probability that I'm going to win gets closer and closer to 1. As the difference in our scores gets more and more negative, the probability that I am going to win goes to 0. So this logit function has the properties that we want. Okay, if the argument represents the scoring difference, the difference in our scores, this function is a way of turning it into a probability. Okay, that accurately reflects that. Any questions about this? Now then, we have a way to update, okay, what you call it, scores, okay, in response to games. And again, the ELO system is most famous for being used in chess, but to compute chess ratings. But it's generally useful whenever you have a stream of comparisons. Suppose I were to be playing Garry Kasparov, okay? Garry Kasparov had an ELO rating of 2,800. I have a rating of 1,200 about, okay? I push wood, I'm not very good, okay? Suppose that we played, and what should happen when Garry Kasparov and I play chess? It should be clear I get slaughtered, right? But by some miracle, okay, perhaps I slipped him something before the match, okay, I won. We had one match, okay. There should be, if we look back at the ELO formula here, okay, my expected value was I should lose. If I won, I had a 1 when my expected value was -1. The difference here would be 2. The number of points that I would change depends upon this constant k. In chess, you can actually never change your rating by more than 80 points on one match. But lo and behold, after I beat Kasparov, I took 80 points from him, okay, because it was so surprising. Any questions? Now, what happened when the greatest woman chess player of all time, Judith Polgar, played our current champion, Magnus Carlsen? Okay, it was a surprise, but Judith won. Okay, it was not anywhere near as big a surprise as it was when I played Kasparov. Okay, and what you call it? She got, I think, on this case, she gained about 55 points based on the differences of the rankings. Okay. Now, suppose I played the winner. I played Judith Polgar. Again, her rankings are incredibly better, much better than mine. Okay? And afterwards, if she beat me, it would do her no good, and it would do me no harm, because I would lose very few, essentially no points, because my win probability should have been so low. Okay? The difference between expectation and what happened was essentially 0. Does everybody kind of get the idea that this shifts scores by a lot when there is a surprise, but by a bounded amount based on that K? Okay? And if I take a stream of data like this, I can compute rankings on everybody on the basis of these binary comparisons. Any questions about that?
Is the ranking an integer?
Is the ranking an integer? I would say that if we take a look at the formula, okay, it should be based on the expected value here. The expected value here is a function of the probabilities, and the probabilities are dependent upon the logit function. This is a continuous function. The ELO thing should return a real number as your score, not an integer. Although for convenience, people probably truncate it just because it's easier to think about integers. But there's nothing in this system that would be inherent to suggest that it should be an integer. Any questions about that?
How do we
Pick A.
looking
Yeah.
at, is that the sigmoid function or the logit function? The function that we are looking at in the previous slide looks like a sigmoid function, or I don't know.
Yeah, so this is like a sigmoid function. In a sigmoid function, it starts low and it goes up and it hits an asymptote at 1. So the logit function is presumably one particular kind of sigmoid function. It's a class of, it's a sigmoid function that is interesting, okay? Note that we could have, if we wanted a richer parameterization here, there's no reason why I couldn't take that z and replace it by some constant times z, okay? Which is actually equivalent to changing the e to a different base. There are other sigmoid functions you can define depending upon how steep you want the transition to be as a function of the score. So yes, this is a sigmoid-shaped function. The logit function is a particular sigmoid-shaped function that is quite convenient, and we will see later in the semester.
How do we decide how to, what the rank will be for the initial thing, like the initial RFA that talked about?
So what should be your initial ranking? Well, one is, if you assume you come in a world where you don't know anybody, you don't know anything about the guy, okay? Then you're probably best off giving everybody that comes in the same ranking at the beginning and let the play that they have correspond, do it later, okay? Now, if I have a new chess player who introduces himself, says, I've never played a match before, but I'm Gary Kasparov's son, okay? maybe you know something and you might want to seed them a higher value at first. But typically in a system like this, if they're going to play matches, they should prove their worth. And you start them at a particular amount. And then once you start it, every match takes points from one person and gives them to somebody else. That's how the system works.
Okay.
Any questions?
Thank
How
you.
do I pick the value of k?
What should the value of k be? Okay. Well, k, if we look at this thing, is measuring what's the maximum amount of swing that you should have in the basis of upsets. If you have too big a value of k, then suddenly one surprise result wildly changes everybody's ratings. If you have too small a value of k, it doesn't react very quickly to changes that, to changes. If you start getting better, it would take you, the system, a while for you to recognize that. So this is a parameter you kind of have to set. In chess, I think k is equal to 40, okay? Typically, they start people, I believe, at 1,500,
1200.
and k is equal to 40. But recognize what the effect of the k is, okay? I can't tell you what the right way to set it is. You want to figure out how much swing you want in your system. That's what the parameter is going to tell you.
Okay.
Does the order in which you do the comparisons in time matter?
Does the order in which you do these comparisons in time that are matter? The answer, I believe, is yes, but actually I don't have a proof in my head, okay? What is the case that, recent results should be reflected here because your score is going to be going up, okay? I believe that the order of the comparisons matter, okay? But I'll admit in my head I don't have a proof of that.
Does that make ELO a bad kind of metric for comparisons that don't have a temporal order to them?
So if it doesn't have a temporal order, that might be, might not mandate this. But a lot of things in the world have temporal order. If you're ranking schools, should the fact that back in 1928, somebody chose Princeton over Cornell, should that have much vote in right now if you wanted to rank schools? Or should the current data be more meaningful? Okay. Often there is a temporal element here. And that I think is something that is captured in these systems. Okay. Any questions about that? Okay, we are over here. Think about it again. Maybe we can have any more questions. We'll talk about that next class.